Hello students, in last class we have discussed the factor affecting the acceleration due to gravity, and we have derived the expression for acceleration due to gravity with height and some depth from the surface of earth. Now we are going to take a topic of effect of rotation of earth on acceleration due to gravity g. So our topic is okay. So as we know that Earth can be considered as a perfect sphere of radius r. Suppose if you draw a diagram, then suppose it is a Earth and having mass m, and its radius is r, and it is a center O, and its radius, and it is equatorial plane, and it is polar axis. Now suppose we want to calculate the acceleration due to gravity at point P, which is at the altitude of, which is at the latitude of angle lambda, this angle lambda, and we want to calculate the acceleration due to gravity at point P. If we neglect the rotation of Earth, then at point P, its acceleration due to gravity due to Earth, it will be towards the center, and which will be equal to simply mg. Suppose an object of mass m is placed at point P. So in the absence of any rotation of the Earth, the acceleration due to gravity due to Earth on this mass will be mg, and its direction will be toward the center. But if we assume that Earth is revolving, then we can consider that every particle on the lying on its surface, it also revolves around the horizontal circle with same angular velocity. Suppose it is omega. So suppose we are assuming that Earth is also rotating like this. So every particle, we are assuming this particle m placed on m, so it will also revolve around the horizontal circle like this of radius. Suppose it is small r, right? So this particle will also revolve around this horizontal circle of radius small r, and we can say since this angle is lambda, so it will also be lambda. So now due to the rotation of this particle about the circle of radius r, a centripetal force acts on this particle, so we can take this force in this direction, which will be m omega square r, where m is the mass of particle, omega is the angular speed at which it is rotating, and r is the radius of the path on which it is rotating. So it will be the direction of centrifugal force. So now net acceleration due to gravity of this particle will not be mg, and it will change by some amount, and it can be calculated by the resultant of mg and this force m omega square r, and the angle between these two forces will be 180 minus lambda. So now we can calculate the acceleration due to gravity at point P, net acceleration due to gravity, which will be mg dash. So we can draw a diagram. We can draw a direction of this net resultant of mg and m omega square r. Suppose it is mg dash, and we want to calculate this mg dash. So we can calculate it by the vector resultant of mg and m omega square r, and as we know that resultant of two vectors can be calculated by this formula: r equals to p square plus q square plus 2pq cos of theta, where theta is the angle between them. So By similar way, we can calculate the resultant of mg and m omega square r, and here resultant will be mg dash root m g whole square plus mr omega square r whole square plus 2 mg m r omega square cos of 180 minus lambda. This will be resultant. Now we can solve it by taking m common. M will be cancelled out from the both sides, so remaining term will be g dash will be root over g square plus r square omega 4 plus 2g r omega square, and as we know cos 180 minus theta equals to cos theta, so we can write it as cos of lambda. Now by this triangle, suppose this point is O P and suppose it is point A. So by triangle OAP we can write cos lambda equals to r upon capital R base upon hypotenuse. So small r become r cos of lambda. So by putting this value of small r in this equation g dash, it will be g square plus r square cos square lambda omega power 4 plus 2 g r cos square lambda, sorry r, so cos lambda only, and omega square cos lambda. Now by taking g common, remaining term will be 1 plus r omega square upon g whole square into cos square lambda, and here actually cos 180 minus theta is minus cos theta, so here minus sign should be there, so here also minus of 2 r omega square upon g cos square lambda whole power 1 by 2. Now if we solve these values by putting the value of r, which is 6400 kilometer, omega, which is the angular velocity, r is 6400 kilometer, omega angular speed, which can be calculated by 2 pi upon time period, so 2 pi upon 24 hour means 86400 radian per second, right, and g, which is 9.8 meter per second square. Now putting these values in this equation, when we calculate these terms r omega square upon g whole square and 2r omega square upon g, then we get r omega square upon g 6400 into 10 raised to power 3 into omega square means 2 pi upon 86400 whole square upon 9.8. So it will be approximately 1.291. So since r omega square upon g, which is this term, it is 1 upon 291. So r omega square upon g whole square, it will be very less than 1. R omega square upon g whole square means 1 upon 291 whole square, it will be very less than 1. So we can neglect this term from this expression, so remaining expression will be g dash equals to g 1 minus 2 r omega square upon g cos square lambda whole power 1 by 2. And binomial expression, as we know, 1 plus x whole power n can be written as 1 plus nx plus n minus 1 upon factorial to x square plus so on. So when we expand this term, then we'll get the higher power of x, and here x is 2r omega square upon g cos square lambda. So as we know that r omega square upon g is very less than 1, so higher power of this term will be very less than 1, so we can neglect the higher power of x. So by binomial expansion we can write this equation as 1 minus 1 by 2 2 r omega square cos square lambda upon g. So g 1 minus r omega square cos square lambda by g. So net acceleration due to gravity by considering the rotation of earth will be g minus r omega square r omega square cos square lambda.